Okay, hello everyone. So in this video, we're going to explore solving inequalities involving modular sign. So mainly it is to open up from the modulus notation into a non-modulus notation when we solve all these things. Now, but before we start, right, we're going to look through 4 possible cases or even 4 basic concepts when it comes to solving for these kind of inequalities. Now, the first one is if a is a positive number, right? Then if modulus x less than a, right? You can be equivalent to this, right? That means when we open up the modular sign, right, we can write this inequality over here, which is x in between negative a to a. Now, why is this so? Is because now let's explore one example, one concrete example. So modulus x less than 2. So obviously, if we look at positive numbers and even 0, right, that doesn't require modulus. These are numbers less than 2, right? However, if you look at negative 1, when after you put in the modulus, it becomes 1, and 1 is actually less than 2, right? If we look at the number 2, negative 2, the modulus negative 2 would become 2, and this is equals to 2. However, if we look at negative 3, modulus of negative 3 will become 3, and this is already more than 2. So this is the value that we cannot have, right? We cannot solve for to get this value because this is an invalid value. So means, right, the possible values for x lie between negative 2 to 2. So this is why when we open up the modular sign, right, x is in between negative 2 to 2. Okay, so means that for a less than modulus, the resulting non-modulus inequality would be the in between. Now, moving on, if you look at the next case over here, if modulus x is more than or equal to a, right, then the result is x is less than or equal to negative a, and x is more than or equal to a. Now, let's take a look at this example. So x, modulus x more than or equal to 3. So let's look at the numbers, positive numbers first. So these are the numbers which are already more than 3. So putting them in modulus, right, would make them more than 3. Okay, so already when we open up, the solution that we get will be x more than or equal to 3. Now, however, if we look on the other side, on the negative side, which numbers when we put in the modulus will be more than or equal to negative 3? So starting from negative 3, then negative 4, all these numbers when you put in the modular sign, right, they will be already more than 3, right? So these are our solution as well. So means that we have two possible solutions or two range of solutions to consider. X more than 3 and x less than negative 3 for this region. Okay, now what about the numbers in between over here? Now these numbers over here, right, now when you put in the modulus, they are less than 3, so these are not the solution that we want. Okay, so take note again. Now, so the more important case that I want to highlight is these two cases. Okay, so the first one over here is where modulus x less than 2, we can open up to negative 2 and 2. So in between negative 2 and 2. Now when it is a more than modulus inequality, when we open up, right, it will be the outside, the less than and the more than region. Okay, now if we want to look at the graphical notation, okay, if you want to look at the graphical notation over here, right, okay, let me draw this out. Okay, and this is x equals to 2, right? So for the less than case, means that we are looking for this region in between. You see this? Right? So the resultant region is between negative 2 to 2. Right? So the x values that we are looking for is within this region over here. Okay? Now in the same way, if you were to look at the graphical method, if you look at the graphical method, the region that we're interested in is this part. Okay, I think I should use different color. Okay, yeah, so it will be this part and this part over here. So mapping back to x, we are looking for this region, and this region, and we'll start from -3 to 3. Okay, so can you see this, right? So these are the range of values that we are looking for, okay, for modulus inequality. Now for the last two case over here, now if a is a negative number, then modulus x less than a is impossible for all the values of x. Now let's take a look at this. Modulus of x less than or equal to -1. Now is there a number after putting through the modular sign that will give you less than -1? The answer is no. No solution, right? Now the reason why there is no solution is because all, so modulus x, right, cannot be a negative number. Okay, so modulus x cannot be a negative number, and because of that, right, there will be no solution for this inequality. Now on the other one, now if a is a negative number, then x more than a is valid for all the values of x. So this one over here, the solution set will be x, all the real number x. Why? When I put this number in, modulus would be 7. 7 more than -3. So all these numbers, when I put in, right, they are all more than -3. Right? All these numbers, when you modulus, they are all more than -3. And the reason is simply because modulus x is positive, right? And this is always more than a negative number. Okay, so this is the idea that we are looking at for modulus inequality. So let's say if it's less than or more than for positive numbers, then we have a solution. If it's a less than negative number, no solution. If it's more than negative numbers, the solution is all the real numbers. Okay? Okay, so one last point over here is that to solve the inequalities involving modulus, several methods we can use several methods over here. So there's the graphical method, there is the definition of the modulus, and we can square both sides as well. So the examples below, we are going to explore each of these methods. Okay, first and foremost, let's take a look at the graphical method for this inequality. So first we have modulus 3x minus 2 less than 4. Okay, so over here, right, we have the modulus graph. So we are looking at the graph of y equals to modulus 3x minus 2, and we are looking at the graph of y equals to 4. So we are comparing these two graphs. So technically speaking, we will need to look at this, right? Y equals to this, y equals to that. Then we are looking at the region for which the modulus graph is below 4. Okay, so this translates to the modulus graph, right? The region where the modulus graph is below the line y equals to 4. Right? So where is the modulus graph below? So from this point and this point, oh wait, we cannot take these 2 points, so this must be an open circle over here. So this region is the one that we're looking at. Right? This region is the one that we're looking at, but we have to look at the x values that will give this region. So what are the x values that will give this region? It will be between -2/3 and 2, right? And it cannot be equal to these two numbers because of this. Okay, so yeah, so the graphical method is fairly straightforward. So I think you can use your GC to get the graph out, and you can get this the intersection, right? So now this method is what we call a two graph method. So where we draw two graphs and we get the intersections, and after that we will look at the region where the graph is either above or below. Okay, so the second method over here that we're going to look at is to use the definition of modulus. So what we can do is we can open up this modular sign. So this is a less than modulus, so means it will be in between -4 to 4. Okay, so what I will do is, now I will make x the subject. So over here, I'm going to add 4. I'm going to add 4, sorry, 3x minus 2. Okay, so over here what I'm going to do is I'll just add 2 to all the inequalities. Alright, so here I will get a negative 2, I'll get a 3x and a 6. Now afterwards, in order to get rid of the 3, I will need to divide by 3. And because of this, I need to do this for all the sides. So, and what do I get in the end will be negative 2 over 3 less than x less than 2, which is same as the answer that we've gotten in the previous part. Now, alternatively, we can also look at squaring both sides. Right? So when we square both sides, we have this square less than 16. So why does squaring both sides work? Because for this particular question, the modulus and the 4 are both positive. So when we multiply or we square both positive numbers, the inequality is preserved. Okay, or the inequality remains the same. Now, so what do we do next is we will expand. Right? And after expanding, we will get something like this. Okay, so at this point, we can divide by 3. And we will attempt to do factorization. Right? And because of this, right? And because of this, you can make use of what you've done in the previous part. So I'm going to show you the number line method for this. Now the boundaries or the critical values are negative 2 over 3 and 2. So for this one, this is for the factor of 3x plus 2, and the one above I'm going to draw for the factor of x minus 2. So this is a positive factor, so I'm just going to draw this direction. This is also a positive factor, I'm going to draw in this direction. Now above the, now I'm going to do this above the, I'm going to put the positive. So because these are the numbers that will make the factor positive, and the region outside is the one that will make the factors negative. So negative times negative will give me positive. Negative times positive give me negative. Positive, positive give me positive. So the region less than 0 is going to be this middle region over here. So therefore, the solution that I have would be between negative 2 over 3 and 2. Right? So this is the solution if we want to square both sides. Now, comparing 3 methods, right? The graphical method using definition of modulus and squaring both sides. So these 3 methods, right? Which method would be the fastest? Right? So I think it solely depends. For a simple modulus like this, right? For a very simple modulus like this, I would definitely recommend method 2. Right? However, when modulus are very complicated, I would recommend this over here. Okay? So definitely between these 3 methods, there'll be the faster methods and there'll be slower methods. So it's up to us to see and judge and like try to make sense, and or maybe like try to be flexible so that we will achieve our results in the shortest method possible. Okay? Moving on to part B, we are looking at this case where x plus 4 modulus is more than 2. So we are looking for the place where, okay, so first and foremost, we are looking at the graph for y equals to x plus 4. And we are also looking at the graph of y equals to 2. So if you are to do the graphical method, you will need to do this on your GC. Okay, so now we are looking at the place where the modulus graph is above the line y equals to 2. Right? So which regions are these? So this is in this region over here, and we are looking at this region over here. Right? So the corresponding x value would be from here onwards and above, and here before. Okay? So therefore, the answer will be x less than negative 6 or x strictly more than negative 2. Okay, So looking at the graphical method, we will be able to determine the range of x for which it satisfies this condition. Looking at the definition of modulus, so if it's like this, more than 2, so when we open up the modulus, it will be more than 2, or it will be x plus 4 less than negative 2. Right? Then it will be just very simple to solve. Right? So then we have our answer like this. Then if we were to square both sides, because we are both these numbers on the left and the right are positive numbers, so when we square them, the inequality remains the same. So then we will expand. Then we will bring everything to one side, like how we solve for quadratic inequalities. It'd be like this. Okay, so the critical values are between -6 and -2. Right, so if we were to use this graphical method for this question, we're looking at this region. Okay, so this is the one graph method, right? So over here, therefore, the values of x would be here and there, right? So this would be x less than -6 or x more than 2. Oh, sorry, -2. Okay, so this is how we solve the modulus for the more than case. Okay, for example C, looking at something a bit more complex. So over here, we are looking at the red color graph, y equals to 2x plus 1. And we're looking at the modulus graph, y equals to modulus of x minus 2. Right? So first and foremost, we will need to look for the intersection point if you're looking using the graphical method, preferably in exact form. Now, over here, we are looking at the place where the modulus graph is above the line y equals to 2x plus 1. So where is it above the line? It will be just strictly over here. From this point here upwards. Okay, it will be just this point over here and before. So the corresponding x, range of x will be before this point, right? So if we were to solve, so x would be more than, less than or equal to 1/3 over here. Okay. Okay, so for the second method, if you want to use the definition of modulus, right? Now this one, usually it is not recommended lah. Okay, so when it comes to just numbers, right, then it will be easiest to use the definition of modulus. But when it comes to algebraic expressions, or when it comes to different forms of lines already, then we really don't recommend using the definition of modulus. Now let me tell you why. Now over here, right, if we open up this, we get a more than the positive version, or will be less than the negative version of this. So this is what we call using definition of modulus lah, right? To open it to a non-modulus form. And it will be easier to solve that way. So on the left, we can solve this to be -3 less than 3x, -1 less than x over here. Okay, and if you look at the other side, we will have 3x less than 1, and x will be less than 1/3 over here. Alright, now then it is a bit inconsistent already, because if we were to look at this solution and this solution, right, now x is less than -1 and x is less than 1/3. Now if we were to look at this solution over here, normally we would need to take this solution, right? Now however, let's take a look at the graph above. Now notice that for this one over here, right, the graphical method, okay, the intersection is only between this y equals to 2x plus 1 and y equals to -x plus 2. Okay, so it's in between this and this graph, right? So technically this inequality would hold. However, this one will not hold because technically speaking, the intersection is actually over there. But this intersection did not happen, right? If you notice again, if for this particular inequality, it is the intersection between the red color line and this positive x minus 2 graph, right? And where did the intersection occur? The intersection will occur over here. And obviously in this graph, when you do the modulus, right, it did not occur at that point, whereas it occur only on this point. So it's not always necessary where we will always use the definition of modulus to open up the expression to a non-modulus form. Okay, so we have to be very careful here. So for the non-modulus form, we only reserve it for numbers. When it comes to expressions, usually we'll rely on graphical method, and the more reliable method is actually the next one. So the third method over here, right, that we're going to look at is to square both sides. Now, in general, we can attempt to square both sides for this kind of situations. Now, but there would be something that we'll need to take note of that we need to see. Okay, so usually this is okay, right? But we'll need to double check something because when we square, we will create an extra solution, right? So we will need to double check all these extra solutions over here. So okay, so first let me expand all this. Okay, now after expanding all this, I will move everything to one side. Okay, and after this I will factorize. Okay, now it will be very tempting. So I think, okay, so this one you do not write this down first. Now it will be very tempting to do this, right? Because it really looks like something that we've solved before, correct? Now, but because this, for especially for this kind of expressions, right, we have to pay attention to the the solution. Like even when we want to solve for the equation, we need to check, right? So instead of using this method over here, where we need to deploy the test point method. Okay, over here we need to deploy the test point method for the original one, x negative, this original modulus inequality over here. Okay, so what are my critical values? My critical values are -3 and 1/3. Alright, so let's sub in, let's pick nice values to sub in. So I'm going to sub x equals to -4 over here. So I will have a, okay, sub x equals to -4, right? So I will have a 6 on the left, right? And I have a -2 on the right. Okay, one more time. So if I put -4 over here, so this one will be equals to 6, +6, because -6 modulus become +6, right? And if I sub on the right hand side, this will give me a -2 over here, right? So indeed, this is more than -2. So this position satisfies the inequality, right? Then the next portion, if I were to choose, maybe let me sub easy number, sub x equals to 0, right? On the left, it will be 2. On the right, it will be 1. And 2 is indeed greater than 1. So this region satisfies the inequality. Last one, I would maybe sub x equals to 1 to check, right? So on the left, this would be -1, right? Once the modulus become 1. And when we sub on the right hand side, this will become 3. And this is less than, so this does not satisfy the inequality. So this one is not the one that we want. So the region that we want would be this region over here. Okay, so it means the solution would be x strictly, oh no, x would be less than or equal to 1/3 as the only solution. Okay, so now this is the most complicated form of inequalities that we'll need to solve. Alright, so one more time we need to take note again. So The superior method would be the graphical method, because very clearly you can see where the intersection is, and you can take the results from there. When we come to using definition of modulus, this is not recommended. Okay, this is not recommended because we will still need to test the values, okay, into the graph, right? And we'll need to be sensitive to see which exact curve that they are intersecting. So in the end of the day, we still need to fall back to the graphical method to determine which inequality are we solving. We are not solving for this inequality because there's no intersection. We are solving for this inequality because the intersection is there, right? Now, then last but not least, if we were to square both sides, we cannot make use of the usual quadratic inequality method to solve. Instead, we will need to use the test point method to test for values, because when we square, we create extra solutions, right? So note, so when we square, especially for expressions, square both sides, we create extraneous solution. Extraneous, I'm not sure how to, but extraneous solution or extra solutions. Alright, so this is the method that we'll need to take note whenever we solve this kind of inequality, where one side is modulus, the other side is not modulus. Now for part D, now let's take a look at the graphical method. So over here, we are looking for the range where the modulus graph is below the line y equals to 3x. So which is which? So this is the line y equals to 3x, and the blue color line is the line y equals to mod x plus 2. So when you plot into your calculator, right, plot into your GC, you see something like this. Now, and then what do? Is we'll look for the region where the blue color line is below the red color line. So it is this region over here, right? So looking below, so the region that will satisfy, right, the region that will satisfy would be this region for x. So x, the solution is simply x greater than 1. Okay, so now in method 2, right, when we use the definition of modulus, right, so what we're going to do is, now we would need to, so this is totally not recommended. Okay, definitely not recommended. So for this particular one, I will just skip this question, because you need to do a lot of testing and you need to think more. Yeah, so it creates unnecessary time wasted. So let's not use this method for this kind of expressions. Alright, now then for method 3, can we square both sides? Yes, we can square both sides, but before we square both sides, right, we need to rearrange such that all the modulus will be just on one side. Okay, so let's square both sides now. Okay, so over here we have this, right? Tidying up, we'll get something like this. And then I think we can simplify the whole thing by dividing by 4 to, dividing by 4 to really help us to see. So let's try to solve. Oh wait, sorry, divide by 4. So this one over here, I have an error over here. Okay, divide by 4. So I have this and maybe this. Okay, sorry, another error over here. Okay, so now what we have would be, because we divided by 4, so this will have to be 1 and, okay, next step, divide by 4. Sorry, divide by 4 will give me this. Divide by 4, divide by 4, right? So I can factorize this. Something like this, right? So now let's take a look at the test point method for this. Okay, so here I'm deploying the test point method. So like we choose one point from each region to test. Okay, so over here I will choose x equals to -1. Here I'll choose x equals to 0. Here I'll choose x equals to 2 to test out the inequality, or test out the sign of the inequality. And then 4 to test for this. Right? So now, first one, on the left, I'm going to get 1 plus 2, which is 3. Then on the right will be negative 3. So this one does not hold. Okay, so this one will fail my test. Now the second one would be 2 less than 0. So this one will also fail my test. Now the third one over here, I'll get a 4 less than 6. So this one fulfills my test. Right? So the region that I'm looking at will be solely the region on the right. Okay, so it's just x strictly more than 1. Okay, so now once again, right, now when we come to modulus for expressions like 3x minus 2, right, it's not a simple number, then I think the graphical method will be the superior method, right? However, you will need to find a way to find the exact value of the intersection. Okay, so this is where solving the two equations would play an important role. Okay. Now, whereas for method 2 and method 3, we don't really recommend them because it is slightly more time consuming, right? However, if the question requires us to use a non-graphical method to do this, then for the first two examples, A and B, I will recommend the definition. For these two, I would definitely recommend squaring both sides, but you have to test each point. Okay. Now, the last kind of quadratic, the modulus inequality that we'll see for the basic case would be like this. Okay, so we have a modulus x minus 2 more than modulus 2x minus 3. So which graph is which? So over here, this one is the blue color one would be modulus x minus 2. The red color one would be 2x minus 3. Okay, so now we are looking for the blue graph, right, to be above the red graph, right? So which region is the blue graph above the red color graph? Over here, within this region, right? So if we were to look at the x values, so what are these x values? So the x values to satisfy this equation is in between 1 and 1.67 or 5 over 3, right, for this question over here. Okay, so the graphical method, very straightforward. Indeed, really, really straightforward. Okay. So now, let's say if we were to find the exact value of these graphs. So I think what we need to do is we need to find the intersection points between these two graphs. Now, we need to take a look. So now, to find the intersection point, okay. Now, so before to find the intersection point before solving the inequality, right? So we need to look at which graph will intersect to which graph. Okay, so the first point over here, right? Now, if you want to be a bit more, precise, right? So this would be the graph over here, y equals to 2x minus 3. So this would be the positive version, right? And then for the blue color one, this would be the positive version, and this would be the negative version, right? So now for this point, which two equations are we solving? We will be solving between this blue color one and this red color one over here. So we'll be solving these two equations over here to get this intersection point, right? Now, then over here, once you get your working, right, you will find x is equals to 1. Okay, now then for the second point over here, right, which graph are we solving? We are solving for this one and this line over here. You see this, right? So means the second point will come from the solution of negative x plus 2 equals to 2x minus 3. So when you solve this, right, you will get the exact value 5 over 3 instead of the calculator value 1.67. right? So sometimes we'll need to do all this because the calculator doesn't give us a nice exact value. Okay, so take note, we may need to find the intersection point before finding your inequality. So sometimes the working, right, will be like this. Okay, we have to present it something like this above. Okay, so I'll just flash up like this. So we need to find the intersection points. Okay, so intersection point number 1, intersection point number 2. Okay, and we'll need to look at these regions to determine our final answer. Okay, so this is the way we do for the graphical method for at least C, D, E, and F. Okay, now using the definition of modulus would be inefficient because we need to consider 4 different cases, right? We need to consider between 4 different cases. So so we tend to not use this method for this one over here, this question over here. Now, however, we can, for this method, right, we can square both sides actually. Okay, so because, right, both of these are positive numbers, so even if we square both sides, right, we will still get a nice answer, right, and we'll get the answer that fits us nicely. So that's the typical trend that we'll see for these kind of questions. Yeah, okay, so altogether, yeah, okay, we'll simplify on one side, okay, and we'll factorize the next step. So we are looking for the graph below 0, yeah. Okay, we're looking for the graph below 0. So over here, for this one over here, right, now the solutions given, right, will be very nice actually. Okay, so we're looking for this region and this region, right? We're looking for the part below the axis. So the x values that we'll need to take are in between these two values. So it will be 1 less than or equal to x less than or equal to 5/3, which is in the solution from the graphical method as above. Now for this question, right, you may need to ask, how come when I square both sides, now my answers are alright? And in the previous one, when I square both sides, I may not get the two answers. Now the reason is because for this question over here, we may see um, um, like both of these are positive numbers. So when we square, right, we will more or less retain the number of solutions. Okay. Now for the other case where we have just one line and the modulus graph, right, we may have only one intersection, we may have two intersections, we may not even have any intersection at all. So that case is the tricky case that we will need to double check every time. So there will be the case where you get this, right, or you get something like this, right, or there will be the case where you get this, no intersection at all. Okay, so that is why when we square, right, we will still need to check the answer to see which case is it, right? Whereas for this method over here, right, more or less they will intersect at either 1 point or 2 points. So the intersections are more or less guaranteed. So that's why we can fall back on the quadratic method to solve this case. Okay, so I hope this clears the air on why when we do that we have to use test point method, why when we do this we have to use this method. Okay, now I think in the end of the day, I think we still to convince you that the graphical method is still superior for these cases. Okay, so fall back to the graph, solve for the intersection points, and from the intersection point determine the positions of the graph where it's above and below. Okay. Okay, finally we are at F, our very last example. So now which graph is which? So assume that you already sketch in from your GC, right? You already plot in your GC and sketch from GC. So this line over here will be y equals to the 2x minus 3, 2x minus 6, right? So this is the positive version. Then the negative version come from here. Okay, now then for the red color graph, this is y equals to 3x plus 1. This would be y equals to negative 3x minus 1, right? So the negative version. Okay, now so to find the intersection points, so I think the first step for us, if you want to use the graphical method, right, you can use GC, right? However, if the points are not nice, we need to find intersection points lah. So where does the intersection come from? The intersection come from this graph and this graph. So the first one is I need to solve for this and this negative 3x minus 1. Okay, so over here, once I solve, x equals to negative 7. Now the second intersection point that I'm going to find is the intersection between this graph and this graph. Sorry, this graph and this blue color graph over here. Alright, so over here, which will be the negative 2x plus 6 intersecting with the positive 3x plus 1. Okay, so over here, when I solve, right, I will have this. Okay, so once we get our two intersection points, we need to look at where the blue graph versus the red graph, right? This is below. Where is the blue graph below the red graph? So the region is here and beyond, and the region is here and beyond. Right, so these regions are the regions that we're looking for. Now, however, the x values that we're looking for are here. Okay, too big. Here, and sorry, I need to be a bit more precise here, and maybe from 1 here onwards, right? So the final solution would be x less than negative 7 or x greater than 1. Okay, so if we were to use the graphical method, right, it will be helpful to find the intersection point. If it's not nice, then we will just read from the graph directly. Okay. Okay, lastly, we don't use the definition of modulus because it's inefficient. Alright, we still fall back to a graphical method anyway to determine which one to solve, so don't bother. Now, over here, what about squaring both sides? It still works. Let's say if you don't want the what do you call that, the graphical method. Okay, so here let's expand. So be careful of the 4. Yeah, you need to square the 4. Yep, plus 9 less than 9x squared plus 6x plus 1. Okay, so let's expand again. Expand. Okay, so over here 5x squared plus 30x minus 35. Just nice, I can divide everything by 5. Then I can factorize this. Okay, and because normally I will still get 2 solutions anyway, so I can fall back on the what do you call this, the graphical method for this plus 7, so negative 7 and 1. Now where are the regions where it's more than 0? Will be here and here, more than 0. So the region that I will take would be x less than negative 7 or x more than 1. Okay, so I hope this video helps you to make sense of how do we deal with modulus inequalities. Now, so let's recap. Okay, so let's recap what did we just went through. Okay, so the definition of modulus gives us these 2 properties, important properties, and for this one, right, we will just observe and say that there's either no solution or the solution is all the real numbers. Okay, now, and then generally we'll solve it with 3 methods: graphical method, definition of modulus, and when we open up to non-modulus form, right, and we can also square both sides, right? So for the very first case where it is a modulus and a number, we can use all 3 methods, right? But the fastest method will be using the definition. Now, if we go on to the next one where we see modulus and an expression without the modulus, so there will be 3 cases over here if you were to observe the graphical method. So there will be the case where we get 2 solutions. So that means if we were to do the squaring both sides, then we'll be lucky that we have 2 solutions, right? Sometimes we only have 1 intersection like this. Sometimes we'll have no intersection at all. Okay, so for this question, the graphical method would be the superior method, right? So what we do with the graphical method is, now what we will plot the graph, solve for the intersection point, and then we'll look at the inequality, solve for the inequality. Alright, so for this kind of case, we need to be extra careful. If you want to square both sides, remember to check using the test point method instead of the quadratic graph method. Okay, last but not least, where we have modulus on both sides, so usually we will get two intersection points, usually. Okay, so over here, we will need to be very careful to solve, right? Which graph gives us which intersection point. Okay, so need to be very careful to solve, and from there observe and write out the solution for the inequality. Now, the definition of modulus would be inefficient for this point, but we can square both sides, and we can make use of this because we still get two solutions anyway usually. Alright, so I hope this will help you to understand how do we solve inequalities with modulus. I hope it gives you a basic understanding, and it will help you to do more advanced questions. Right, so we end this video over here. Have a nice day. Bye.